Great. So thank you so much for joining, everybody. I'm really excited to have you here and speak to all of the summer school participants about applying to Gemini Observatory. Um, so the goal of this session, I guess, is to tell you a little bit about Gemini and how you can apply for time at the observatory. And then my understanding is that you'll have your summer school and you'll kind of develop science programs for Gemini that's kind of precursor science for future GMT programs. And then I think we'll all meet back for a proposal writing workshop in late August, which hasn't been scheduled yet, but it should be scheduled soon. And And in that workshop, Gemini staff scientists will look through the proposals that you've been working on in groups and kind of think about ways to strengthen your science case or flesh it out and work to make your Gemini proposal successful. So we're really excited to have you all as potential new Gemini users and tell you a little bit about the observatory. And I'm joined here by Jen Andrews, Zach Hartman, Brian Lameau, and Atsuko Nida, and how the structure of this all is going to work today is that I have some slides on the observatory and writing proposals that should take me about 30 to 40 minutes to talk through. Then we'll have Q&A with the panel, Jen, Zach, Brian, and Atsuko. And that will be a chance to answer any questions that you have, either stuff that was brought up in the talk or stuff that was not. And then after that, there will be a Q&A with summer school students only, just to give the students a chance to ask questions. Those students are encouraged to ask questions in both of the Q&A sessions. As I mentioned a minute ago, this will be recorded, but once we do the students only, we will not record. And for the Q&A session, we're not going to share that recording. We're just going to keep it so that there's a live transcript that can be shared in a brief summary, kind of written up in an anonymous way. So with that, I think that was everything. Let me get started with the slides. And please let me know if I forget anything. Zach is going to be moderating the chat, letting people in from the room, and he'll tell me if there are any questions, comments that should be addressed during the talk. So Gemini is 2 telescopes. We have 8.1 meter telescopes in Chile and Hawaii. The telescopes span the range of optical and infrared capabilities, have both imaging and spectroscopy, and Korea is one of several international partners in the observatory. So in the first part of this talk, I'm going to spend a bunch of time on the capabilities of the observatory. First, just kind of a broad overview, and then specific instruments and science cases for those instruments. And the idea being that hopefully this will help you kind of flesh out the science that you might do with the telescope and kind of get you starting to think about your potential proposals and science programs. So as I mentioned, our capabilities span the optical and the infrared. We have imaging capabilities with up to, I think, actually 6-ish arc-minute field of view. We also have speckle imagers, which I'll talk about later, which are very short exposures on time scale shorter than atmospheric variation. So it allows you very high resolution. We have spectroscopic capabilities, including integral field unit spectrographs, where every pixel in your image becomes a spectrum. We have multi-object spectroscopy, where you can simultaneously get spectra for a few different objects in your field, and high and low resolution modes. And I'm not sure of the experience level of everyone in the room, so I'm going to try and kind of introduce all these capabilities from a relatively new to Gemini perspective and new to observing perspective. And hopefully we can get at any questions you might have in the Q&A. And for high resolution, we have adaptive optics systems, which use laser or real guide stars to correct for the atmospheric distortion in real time and give us really high resolution imaging or spectroscopy. And I'd encourage you to check out our capabilities brochure. I believe I shared the link to the slides with you previously, so you can click on these links after the session. So just to dig in a little bit more on the capabilities at Gemini North, we have in the optical GMOS, which I think is our most used instrument. It's a imager and low resolution long slit integral field unit or multi-object spectrograph. It has all those capabilities. We have Alopeka, which does speckle imaging and also wider field, very rapid imaging for things that are changing on short time scales. And MaroonX, which is a red sensitive high resolution spectrograph, particularly optimized for radial velocities. In the near infrared, we have GNIRS, which is single slit spectrograph, and it also does what's called cross dispersed spectroscopy, where you have the different spectral orders across your CCD, which can allow for very high resolution or long wavelength coverage. And we have a relatively new integral field capabilities on GNIRS as well. I know Brian, who's on the call, has worked a lot on this. And Zach, who's on the call, has worked a lot with Alopeka. For adaptive optics, we have Altair, which can only be used with GNIRS right now. Previously, it could be used with a couple instruments that are not currently being offered for proposals, but that will be expanded in the future. And then in the south at Chile, we have GMOS again, a copy of this very commonly used imager and low resolution spectrograph. We have our brand new instrument GHOST, which we're really excited about. I'll talk more about that in a minute. It's a new high resolution spectrograph. Zorro, which is a copy of Alopeka in the north, a speckle and rapid wide field imager. And in the near infrared, we have Flamingos 2, which is an imager and a multi-object spectrograph, the Gemini South adaptive optics imager. We also have IGRINS, which is a high resolution spectrograph in the near infrared. And our adaptive optics system is the Gemini multi-conjugate adaptive optics system, which is currently only with the GSAOI, but will be able to be used with Flamingos 2 and GMOS in the future. So that's kind of your broad overview. I'm going to dig into these different instruments just so they are a little more memorable and not just a list of things, and talk about some of the science cases for these different things. And so hopefully this will be a chance to think about the science possibilities. And I'm not sure if I will have covered everyone's science areas, but I'll do my best with these slides. So GMOS has both imaging and spectroscopy. The imaging is UGRIZ. That means it spans from the near UV to the infrared, includes long slit, multi-object, and integral field spectroscopy across this optical range, a 5x5 arc-minute field of view. And if you're doing integral field spectroscopy, again, where each of the pixels in your image is its own spectrum, then you have a much smaller field of view. The potential science cases are numerous, as you might imagine from our most used instrument. Astrophysical transients in particular, that's something that I work on. You often don't need high resolution spectroscopy to determine the properties of your supernovae, as they often have very broad absorption lines. But GMOS can also be used to characterize AGN, study high redshift galaxies, and so many other science cases. And the one that I've kind of identified here is perhaps a less commonly used GMOS science case, where GMOS was used with a high resolution grading for stellar radial velocities. And with those radial velocity measurements of a nearby star, observing how those velocities changed, astronomers were able to identify the presence of a hidden companion, the most massive black hole nearest to the Earth. Did I say that right? The closest black hole to the Earth. That's what I meant to say. And so you can see RV is a function of phase, where some of these GMOS measurements come in red. Then we have GNIRS in the near infrared. So this can cover a massive wavelength range from 0.8 to 5.4 microns. The resolution ranges a lot too, depending on the wavelength coverage that you're getting, and a 5 arcsecond by 3 arcsecond IFU. And this is another instrument that I've used in the past for supernovae, particularly for studying the nucleosynthesis, how elements are formed in the aftermath of the explosion. But it's also great for AGN, stellar mass loss, high redshift galaxy evolution. And to this last point, this press release used both GNIRS and GMOS to measure the redshift of redshift 2.1 quasars and constrain their black hole masses of these two merging galaxies. So this was a case where at redshift 2, GMOS was able to be used in the right-hand panel to probe the rest frame ultraviolet, whereas on the right-hand side, GNIRS was used to probe the rest frame optical. And so you can kind of see in these panels, the rest frame wavelength is along the top here. H beta and H alpha are identified in this GNIRS spectrum, and the GMOS data is used in the ultraviolet. So this was a way to get a redshift identification, characterize black holes, and study galaxy evolution. Alopecia and Zorro are these speckle and wide field rapid imagers. They can get really, really high resolution in speckle mode, up to 0.025 arc seconds. They have a limiting mag of about 18 to 19. Data reduction is provided for speckle imaging, which can be complicated. There are lots of potential science cases, anything you can imagine where you have a reasonably bright target and you could really, really use high resolution. So exoplanet, host versus star characterization, stellar astronomies, binary systems, quasars where you want high resolution of the environment. And I think this press release is a great example of the types of things that Alopecia and Zorro can be used for, where they looked at a very crowded region at the most massive known star in the galaxy. And looking at this region, they saw that the previously identified most massive known star was actually multiple sources. And at the end of the day, it was still the most massive known star, but I think it was nearly a factor of 2 less massive. So that tells us a lot about how stars evolve and the maximum mass that they can have. Then next we have GHOST, which is our newest instrument in Gemini South. This is a fiber-fed optical spectrograph, high resolution with coverage across the optical range. It can do 2 targets simultaneously, as long as those 2 targets are within 7 arc minutes. The signal to noise can go down below 17th magnitude in reasonable exposure times. And this instrument is just now becoming available to the community. So there's going to be a shared risk call for proposals in late August. And also you can propose for 2024A observations. And if you're particularly interested in GHOST, please check out the GHOST webinars, which are going to be this coming Thursday and Monday, followed by a couple additional webinars. So please go to the slides and check out this link if you're interested in knowing more about GHOST. GHOST is particularly good at using it to learn the chemical compositions of stars and galaxies, exoplanet atmospheres from transit spectroscopy, interacting binaries. There are lots of great science cases outlined on the GHOST instrument page at gemini.edu. So I'd encourage you to check those out as well. And this is a plot on the right-hand side from our first science results, which is using GHOST to measure chemical abundances for peculiar stars enhanced with our process elements in a nearby galaxy. So in the blue and the red, these are stars in the nearby galaxy Reticulum 2, and you can use those chemical abundances to study the processes of stellar and galaxy evolution. GSAOI, the Gemini South Adaptive Optics Imager, is a near-infrared imager. It can cover from 0.9 to 2.5 microns with the variety of broad and narrowband filters. Similar to Alopecia and Zorro, it's good at cases where you really need high resolution imaging. So that includes resolved stellar populations, AGN environments where you want to study those environments in high resolution, crowded regions like the galactic center and the bulge. And I thought this was a cool use case of GSAOI, where astronomers witnessed a potential star devouring a planet. So this was a case where the actual incident of the star devouring the planet was observed with the Zwicky Transient Facility. And then after, so this shows the flux difference as a function of time, and ZTF observed this object go off. And then after the transient had then faded, they were able to go back with GSAOI and look at what actually resulted from this merger process and characterize the star that remained. IGRINS, this is a high resolution near infrared spectrograph covering about 1.5 to 2.5 microns. It's great at characterizing solar system objects, young stellar objects, metallicities, exoplanets. I might get myself into trouble here because I know next to nothing about solar system objects, but I thought this was a nice case where IGRN spectra were used to identify the signature of a CO-N2 ice blend in Neptune's moon of Triton. And in this plot, this just shows the spectrum in red from IGRNs with an absorption line here that was indicative of that ice blend at 2.2 microns. So I don't know too much about solar system objects, but definitely worth saying that Gemini does a lot of really cool solar system science as well. Maroon X, which is a red sensitive high resolution spectrograph that's particularly good at radial velocities. So this is great for binary systems, exoplanets, their atmospheres, and this science case on the right-hand side is an example of using transit spectroscopy where a planet passes in front of its host star to study the chemical abundances in the atmosphere of this exoplanet. And so this is on the top, this is the actual spectrum from Maroon X. A lot of data processing was done to then unlock the chemical abundances that are shown in this bottom panel for different elements. Last but not least, yeah, this is the last of the instrumentation for Gemini, Flamingos 2, which does near-infrared imaging and spectroscopy. Spectroscopy at lower resolution than some of these other instruments. It's good at studying galaxy evolution, transients, variable stars, stellar populations. And this science case here was where the potentially most powerful explosion ever recorded was observed about a little under a year ago now with a gamma ray burst and potentially a supernova component as well. But the problem was that this explosion occurred in a really reddened region. So seeing through the dust required a near-infrared imager. And with those capabilities, you can study the properties of this transient event and potentially its host galaxy environment. So that's a summary of the instrumentation, and there are several people on the call who are more experts on this instrumentation than I am. So please ask lots of questions about these different modes, and hopefully that kind of gave you a preview of some of the science that you're able to do with Gemini Observatory. So I wanted to talk now a little bit about what observing at Gemini is like, the process of kind of preparing a program, writing a program, how to propose for the telescope. So Gemini is different than many other telescopes in that most of our programs use what's called a Q observing mode. That's where the observations are carried out by Gemini staff members. And our programs are prioritized by how they're ranked by the time allocation committee, where band 1 is our highest priority program and band 3 is the lowest priority. And this Q observing mode saves you some time as the proposer. It's good for targeted opportunity observations, but it does sometimes make you a little bit more disconnected from the telescope and the process of observing, which is why we're doing webinars like this and more in the future to kind of communicate, introduce you to the Gemini staff and talk about the facility and the resources. In addition, we have priority visitor mode, which was recently restarted after COVID, and that's where astronomers can visit Gemini in person to observe their program. This is for band 1 programs only. And the idea here is that if you're here in person, then your program gets priority. We only ask that if you can observe your program because the weather is too poor or the conditions aren't right or your targets have set, that you then observe other people's programs as a secondary option. And then we have normal classical mode observing, like many other telescopes, where you're allocated your certain nights on the telescope and you observe yourself. And we're hoping to have future funding to bring students out for priority visitor mode, but that's still pending. We get a lot of questions from the community about how this Q observing system actually works. So just to kind of summarize this, our goal is to complete as many band 1 programs as we can. And if you have a Gemini program, the odds of completing that program increase if your program is prepared early. It also helps to check in with your contact scientist, have targets that are up both early and late in the semester. Basically, the easier it is to observe your targets, the easier it is for the observatory staff to observe your program. And just to kind of give you a sense of things, the typical completion rates for band 1, 2, and 3 programs historically are about 70%, 50%, and 30%. And this is just an average. I personally have had a lot of good success with band 3 programs, just by having bright targets, a lot of targets that are up at different times during the semester. If you strategize with your program right, you can really take advantage of some of these maybe slightly less optimal windows of weather. And what the actual Q program scheduling looks like is shown on the right-hand side, where different programs from different Gemini proposers are slotted in this plot. Targets have different air masses, so we try to optimize when each target is observed, what programs are observed, prioritize band 1, but also observe the other programs. So it's a complicated process. And because it's so complicated, I had to add that we even built an entire card game around our queue scheduling system. So in future national meetings, we hope to hand those out to all of you. And the idea is that in the game, you and your friends are in charge of queue scheduling. It's more fun than it sounds. And it mostly follows our real rules for how to schedule observations. So you can actually play this online at gemini.edu/GCG, but we hope to see you at a future Korean science meeting and be handing out card decks. But the other nice thing about the game is that it also kind of introduces you to some of the instrumentation capabilities and targets that might be suitable for those different instruments. So there are many ways to actually propose for Gemini time. The one that most people are aware of is our regular programs, where there's a call for proposals once per semester. The next one is going to be at the end of September. And typically for the semester after that, it'll be in something like March. Your programs are evaluated by national time allocation committees. And then you start getting your data about like 3 or 4 months after you initially propose for your program. But there are lots of other ways to propose for time. One of those is the large and long programs, which you can propose for through the US Time Allocation Committee. And this happens about once per year. It's generally for more ambitious science cases that can't be necessarily completed over a single semester due to how much time they take or needing a long time baseline. The fast turnaround programs I'm going to tell you about in the next slide, but there's director's discretionary time as well, which I think is typically maybe new objects, new high priority science cases that weren't anticipated. Can be a variety of science cases though. And then poor weather programs, which I think the community generally isn't as aware of as they should be. But this is the case where you can propose for a poor weather program if you have bright targets, if you can tolerate poor seeing or clouds. You can propose for these anytime. They'll be, they can be observed in poor conditions. If it's a particularly bad weather semester in Chile or Mauna Kea, you can get a lot of great data from these. So the fast turnaround program in particular, I really would like to emphasize. These are proposals you can write that are generally kind of short, self-contained projects. They might result in publications, or maybe you have an idea that you're not sure if it's going to work, but you want to test it out. If you want to follow up an unusual or unexpected astronomical event, or if you just need a little bit of data to finish your paper, to finish your thesis project, then that's a good case for fast turnaround proposals as well. FT proposals have deadlines at the end of every month. As part of this, you as a proposer agree to review other FT proposals that are submitted in the same cycle, and the results are announced within about a month. Your observations are taken within about 3 months. And I emphasize the fast turnaround proposals, particularly because for new proposers, this is a good way to get TAC feedback on your proposal, time allocation committee feedback on your proposal. And also to have the experience of serving on a TAC yourself, evaluating other people's proposals, learning what works, what doesn't work, how you want to write your future proposals to best make the case for your science. So just some quick outlines of how you go about writing Gemini proposals. There are a few pieces. One is the most important part is your one-page science justification with 2 additional pages for your figures and any references that you need. I'll talk a little bit more about that. But in addition, you'll have a 1-page technical justification, which is basically where you say, this is the exposure time we need, this is the configuration that we need, here's how these configurations are right for my science, and it allows us to achieve the proposed goals in the science justification. There's also a second PDF attachment. The first PDF attachment is all anonymous. You won't say at any point who you are. And in the second PDF attachment, you'll talk about the expertise of your team, any relevant publications or past use of the resources. But primarily the TAC, by and large, the TAC ranks totally based on your science justification and making sure that you can actually achieve that science justification with the technical details. The templates for these attachments are available on our website. They are linked from every call for proposals. As I mentioned before, these are primarily evaluated based on scientific merit. The proposals must be anonymized, so you can't say who you are, but I think people think a little too hard about this anonymized part sometimes. You can still cite your papers, you just can't say that you are the one who wrote those papers. You can still make your case the same way you would do for any other proposal. And there are some modest differences for other proposal types. So we'll go through at the proposal writing workshop some more general advice for how to write your proposal. And I'm sure some of this might be talked about in the summer school as well. But I just had a few slides to talk about the general procedures and goals for writing a proposal. First off, you want to make your proposal understandable to a large audience of astronomers. Everyone who reads your proposal will be an astronomer, but they won't necessarily be experts in your specific field. And so this was an example from a proposal that I was a co-I on that I thought was particularly nice. This is just kind of the introductory paragraph of the science justification, where they start with exploding stars and other astrophysical transients touch almost every aspect of astronomy, from stellar evolution to galaxy formation to gravitational waves to cosmology. So starting hugely big picture, and then from there, going down into your science case, which should loop back a little bit to say why it's important to the field as a whole. So that's something to keep in mind. In addition, feasibility is really important. And in particular, using the Gemini integration time calculators to evaluate your targets and make sure the TAC knows that the science that you're proposing to do is science that you're able to do with Gemini. So this is a proposal that I wrote on the right-hand side. This is the signal to noise ratio as a function of wavelength for G-near spectra. And then the text here is from my technical justification, where I talked about how these ITC results plus the configuration that I wanted are appropriate for the observations that we'd be obtaining, helps to they're characteristic of a typical target in this program and will help me achieve the science goals from this program. And why Gemini is special for this science case is also useful. Thirdly, figures. I think new proposers sometimes don't always think carefully enough about figures. It's different from writing a figure that would go in maybe a science paper. If you imagine your TAC reading a lot of proposals, your figures, they should be compelling and kind of easily understood. So even without absorbing all of your text, your TAC can kind of look at these figures and understand what you're trying to do with Gemini. So I have, I guess, an example from one of my proposals that I don't think is a perfect figure, but hopefully it'll give you kind of an idea of what I mean. This is supernova rate as a function of redshift. And basically we have in gray previous supernova rate measurements. In red and blue, we have some physical constraints. This is the fraction of prompt type 1a supernovae and how they would affect the rates at different redshifts. And then in red, this is what the proposed program would contribute. So you have kind of the context of the field, the physical interpretation, and what this new program will add to that understanding. So again, I think there are things I would change about this figure potentially, but I really want to thank Brian for providing a couple examples of what he said were bad figures, so that we could have that example for people as well. And I have written a lot of proposals with some very, very bad figures that I didn't particularly want to show all of you. So thank you, Brian. This is an example of hard to read figure. The text is particularly long. It's hard to just kind of look at and interpret. It's a big field on the sky. I mean, honestly, Brian, this figure is not that bad. I've seen figures like this all the time, but just the interpretation of what the yellow is versus green versus blue, it requires a lot of kind of thought and interpretation, I guess. And here's one more, which is a very, very long caption and shows equivalent width of 2 different lines with lots of different named targets. You have to kind of understand what morph's average is here in blue. So generally your TAC reviewer, when they're on their 20th proposal and looks through and sees this, they might groan a little bit. So thank you so much, Brian, for that again. Those are some things to think about for your figures. And last but not least, I think I said this already, anonymity. You can't say who you are in your proposal, but I just want to stress that you can still make your science case. You can still cite your past work. You can still talk about your past work. You just can't say that you are the person who's done that work. Using the phase 1 tool. So Gemini proposals are submitted using the phase 1 tool, which we call the PIT. And phase 1 is how we refer to the proposal submission process, where phase 2 and 3 are observing and data reduction, respectively. The PIT can be downloaded from our website, and the goal of the PIT is just to provide an interface for attaching these different PDF documents for your proposal, providing the target information, and submitting all of this together. It's a little bit complicated, but there's what I think is a really good online tutorial video. One of the main things I just want to emphasize is don't try and figure out the PIT on the day that the proposal is due. Just give yourself a couple days to make sure you can load everything in, and maybe contact the help desk if you have trouble with anything. And on that topic, getting help, please, if you need help with anything related to Gemini, please first check out the website. And if you can't find answers to your questions on the website, all our requests for support now go through one place, the help desk system. And this link here will take you straight to the help desk if you have any questions about anything related to Gemini. In addition, you're welcome to email me for help, especially stuff related to this talk, but also any issues with the website where you find it confusing or the content is unavailable or hard to find. I'm a good point person to work on those things. And that is pretty much it. So I want to just end by saying that we'll hold a proposal writing workshop in late August. We haven't scheduled that yet, but we will very soon. Our kind of idea here was that you will send us your proposals ahead of time. Gemini staff scientists, volunteers will read through those proposals, discuss them with you, how you might improve them. And we'll have kind of a general Q&A session and discuss some more general proposal writing recommendations. And we hope to have more junior scientists as Gemini PIs. We hope to help you guys use the telescope and accomplish your science. And we're just really excited to have more Gemini users and junior scientists in particular. So with that, thanks for your time. We're going to move into Q&A.